Yeah, hello everyone. Thanks for joining our talk. I'm here with Nico from Aqarios, representing BMW Group, but also both coming from the Q Challenge project, which started like 3.5 years ago. Is currently in the process of ending. And within this project, we evaluated the use case of sensor placement in our plants. And we want to talk about the hyperparameter analysis we did for that use case together with Aqarios. The whole reason for that use case, the background of it is that in our plants, we want to let the vehicles go autonomously from the end of the production line to the distribution zones outside of the plants. And we want to do that without using the sensors that are built within the cars, because the sensor configurations and setups in the cars, they are all different, and we want to have a consistent and high quality navigation of the cars in the plant. And therefore we need to implement the sensor infrastructure within the plant infrastructure, which means that we need to position sensors throughout the entire way the car will move from the end of the production line to the distribution zone, which is somewhat around 1 kilometer or something. And we need to cover that area on a very, very high resolution level because we need to see objects that are as small as like 30 centimeters or so. And the goal is obviously, and with that I come to the next slide, the goal is to cover this whole area while minimizing the number of sensors, because each sensor is associated to quite a high cost in purchasing first, but also in maintenance, like the electric bill and all that. It sums up quite heavily, because we are talking about hundreds of sensors eventually when coming to that large area to cover. The figure you see there is one of the examples that we actually evaluated. Nico will show which one exactly later. The resolution here is on another level than what I just said, on a couple of orders of magnitude. So the number of possible sensor positions is depicted in yellow, which are, I think, like 20 meters apart from each other. And the blue dots are the street points on the road that need to be covered by the sensors, which are apart, I think, 4 or 5 meters from each other, which is obviously different from these 30 centimeters requirements that we have in real life, but is coming close to it. And this is exactly what we are aiming for, because we have some scenarios evaluated that are actually real-world inspired scenarios. The challenges of that use cases are obviously that the solution space is significant, because we, especially when we increase this resolution I just talked about, we come up with like millions and billions of different possibilities, what sensors we need to activate in order to cover what sets of the points on the floor. And therefore, at some point, classical solvers actually struggle to find a solution for that problem, an optimal solution. Therefore, quantum computing has a good way to find an improvement as soon as it's actually there, like as soon as the technology matures, which is obviously not today, but as we all know, after a long conference in the last couple of days, this will come soon. Right, and the goal is obviously at the end that we save a couple of sensors in order to get some cost cuts compared to the solution we have right now. Right, and with that I hand over to Nico, and he will tell you something about our formulation of the problem.
Yeah, welcome also from my side. So I will talk now a little bit more about the implementation that we did on quantum computers, and I will start as why we want to use quantum computer in the first place. So Marvin already mentioned, for really real scale problems where we have a very low density of the street points and LiDAR positions, classical solvers struggle to find the optimal solution, so there's a lot of potential. And quantum computers can explore this whole solution space differently, because they use superposition, where they can see a lot of solutions at the same time. And also this tunneling effect can jump from one local optima to another one, maybe even a global one, and in this way can be in the future, when the hardware is matured, more efficient. And the Cubo formulations for this kind of problems are well known, so that's very easy to implement and can be used for quantum annealing. And also there are QAA methods. We already heard about it in the last talk, especially with this constrained mixers, who can encode it more efficient than in a Cubo formulation and run on quantum gate model computers, and that can maybe be a good approach in the future. However, one thing is very clear here: there's no general speed up known for this type of problems. We still think it's a good way to investigate in that more. Just because there's no theoretical speed up does not know that there will be better solutions in the future. And one downside is always that handling constraints and embeddings is difficult for this type of problems. Luckily here we have only binary variables, that makes it easier. But still with constraints, quantum, especially these Cubo formulations get a lot larger. I will tell a little bit more about that here. So the objective is that we want to minimize the LiDAR, amount of activated LiDAR. So xi is a variable for each LiDAR position, and this is 1 if there is a LiDAR, and the sum then tells you the number of LiDAR placed. And then we have the constraints, and in the classical formulation we can just use it that for each street point vi, there has to be at least one neighboring LiDAR position where a LiDAR is placed. All right, so we go over all these street points, and for every street point we have one of this inequality constraint. And if we want to bring this into the Cubo formulation, it changes a little bit, but this is actually like an equivalent formulation where we introduce a slack variable yi to cover the cases where we have more than one LiDAR placed, and then we need this penalty terms as a quadratic sum. So here, if in any case, if there's no LiDAR, or then there will be like a penalty term, and in front of that we have a penalty factor that will be important later, because the penalty factor can be chosen in order to make this process better. Usually you want to choose this a little bit higher, because you have to have it high enough that all the optimal solution of the Cubo is also like the feasible solution. But we will see later that there's place for optimization here. Here we have the result of the hyperparameter optimization. That was a very big part in our project. We found that the default parameters are not optimal, and we could improve the solution quality a lot. So one thing that made maybe the biggest difference was exactly these penalty factors. You can see it at the bottom. There we have like all these different penalty factors tested, and a lower value is better. And that was surprising for us, that like very low value around like below 1 achieves the best results. Even then we had a lot of not feasible solutions, but in the end the solutions that were feasible were better than before. Also, the chain strengths and the annealing times make a difference. So the chain strength is when you find an embedding to make sure that multiple physical qubits that are connected to one logical qubit have the same value. And the annealing times, we increased it a lot, and with longer annealing times we get better results. And on the right side you can see it. So at 0 you see always the optimal solution. In green you see the solutions found by quantum annealing with the default parameters, and if it's below 0 then it shows how much additional leaders are needed to cover this whole area. Actually this problem, real 5, was the problem that we saw on like I think 2 or 3 slides before. That is actually like really close to real world problem, just like higher density of like, for example, the street points I think were like 3 or 4 meters between 2 street points, and in real world scenarios we need like 20 centimeters. So it's like 1 order of magnitude difference. But what we can see here, and what's really cool, that with the optimized parameters, we find even for the smallest real-world problem or real-world inspired problem an optimal solution. And for the other problem, we found way better solutions than before. So that is one takeaway. This hyperparameter optimization can help a lot to find better solutions. Then we use decomposition because quantum annihilers still are limited in size, and full-scale problems cannot be embedded on the hardware. So in this case, we decompose this problem into 8 sub-problems. The full problem would have around 4,100 qubits to solve it in like one run, but with these 8 subproblems, like the subproblems had around like 600 or 700 variables, then we can put it on real hardware. And the good thing is you can imagine like when you find a feasible solution for every subproblem, where in every subproblem all street points are covered, then if you put it together, the solution in the end is also feasible. One thing, of course, that's a downside of it, it has not to be optimal, because sometimes if you consider the whole problem, you can optimize the lidars in a better way to use less lidars in general. But the difference is not too much. And in theory, arbitrary big problems can be solved like this, because you can choose arbitrary many subproblems to decompose it. So that's a very nice technique to already consider larger problems that are even closer to real world. Yeah. So the takeaway from this part is classical solvers still outperform quantum today. We can scale it there a lot higher. Also, you saw before that we could find always the optimal solution with classical solvers to see how close we get. And the main bottleneck are the constraints. For unconstrained problems like max cut, we already find that quantum annealing is a little bit better in many instances as classical solvers, but this max cut problem has, as best to our knowledge, no real-world applications. And in real-world applications, you always have constraints, and then you have to formulate it with penalty terms, you have additional slack variables, and then the performance goes down by a lot. And maybe we can learn a lot of this, because depending on what kind of constraints we have and how many of those, we can already have a very good prediction if this problem is useful or fit good to quantum computers or not. And yeah, classical solvers, on the other hand, can handle constraints very well. Even in most cases, the problem gets kind of easier, because the constraints limit the solution space, what means that it's easier to find the optimal solution. So then we, of course, think about how can we handle constraints better on quantum computers. And there where QAOA comes into play. We already heard about it in the last talk. In this use case, we implemented 4 different QAOA versions. In orange, you can see the default QAOA that just uses a QUBO formulation. Then we had a so-called QAOA ansatz approach. It's the same idea that we heard in the last talk with this constraints preserving mixer Hamiltonians. We did it with a one-hot and a binary encoding. And then we found a custom QAOA approach, really tailored to this specific use case. And you can see here really nice in the violet line, the runtime is very slow. That's mainly because we have a lot less slack variables. And this custom approach found the optimal solution for all these instances considered here, while, for example, the default approach only already had a runtime around 1 hour, so it's seconds on this Y scale there. And we had a timeout of 1 hour, so the bigger problems we could not even consider. And the default QA could not even find one optimal solution for any of these use cases. So there, I think there's a big opportunity to use this constraint mixer Hamiltonians in the QAA, especially for this use cases with a lot of constraints, and a lot of times if you do like a custom approach for this specific use case, it works a lot better than just doing like plug in and play, so to say, approaches. So what's our conclusion? We demonstrated the impact of hyperparameter optimization and decomposition. So there you can already tackle very large instances for use cases like this, but classical solvers are still ahead. There's still like a long way to go in this area to really come to a quantum advantage. But what we think that like this use case specific QAOA versions maybe will be the first thing that could work, especially because a quantum gate model evolved very quickly right now. And for especially use cases like this, the potential of cost saving is really, really large. So this maintenance costs each year are large, and classical solvers cannot find the optimal solution. So there's a great opportunity to do more research about this topic. In this use case, we are already on the way to implement it also in the Quark platform from BMW. It's kind of finished, maybe end of this week or next week we will publish that. And we have an app in the Q Challenge project that will also be published maybe next week. The project only runs until the end of the month, so it will be very soon, where you can see all these different use cases, for example, sensor positioning, and just play around, see how it works, see the solutions for it, and so on. And then at the end, we have a small joke. You can read through it, and then we are here for questions.